Okay, that's good to know. SQLite makes no distinction whatsoever. There's no optimization fence there that optimizes it. So yeah, so what Bruce is saying is that with Postgres, apparently, this lower expression, this right here, this select, because it's a subquery, there might be some transformations to bring that subquery up and make it a part of a join at a higher level query, which could possibly run faster. And you're saying Postgres it deliberately does not do that because it considers the common table expression to be a fence, optimization fence. We've got a question behind you.
For those people who,
Yeah, you're on.
for those people who are overly worshiping normalization, when we end up doing join, what's the difference?
Well, this is all it's a matter of presentation. It's a matter of being able to present the code in a way that it's easier to maintain. Another way of thinking about common table expressions would be this code, where I've created a temporary view, then I'm using the view, and then I'm dropping the view.
I think the classic case for this, I think maybe you have a slide later, but a case where you want to compute some result set first and reference it multiple times.
Right. So the idea might be that it's going to force it to materialize the view, and then it will be used in a join or something like that.
Or no, you might reference it multiple places.
Or use it in multiple places, and so you don't have to type it twice.
Multiple subqueries.
Yep.
There's really no good way of doing that except that.
Well, but you can do it with a temporary view.
Right. I mean, in one query.
But in one query.
Right.
Okay. So, but logically, these are the equivalent. And so, apart from some syntactic sugar, ordinary common table expressions aren't all that exciting. What really gets interesting is the recursive common table expressions. Before I get into that, let me just pose a hypothetical problem. I want to fill some table with all integers between 1 and 5. And if you're new to SQL, you might think that you could do it this way, and I'll explain in a minute. But before I even get started, let me just go ahead and cut off the objections that SQL will not work like what I'm going to tell you it is. But if you're new and you've just come into SQL, you might think it would work this way. So we create the table, and we insert a seed value, and then we have an insert here that selects data from itself, and it's sort of a self-insert. Insert into T1, select X plus 1 from T1. So we start out, and table T1 has a single value in it, which is the number 1, and it hasn't read anything yet. So the first thing it does is it reads the 1 up here in the select. It reads the 1 out of T1, it adds 1 to it, and inserts it into T1. And so now you've got 1 and 2 in the table. Okay, and then it keeps reading, and it reads the 2, and it adds 1 to it, and it inserts a 3 into the table. And so then the cursor keeps reading, and it reads a 3, and then adds 1 to it, sees that 4 is less than 5, so it inserts the 4 into the table. And it keeps reading, and then it adds 1 to 4 and says is 4 less than 5, or well, no, it's 4 less than 5. It is, so it inserts a 5 in the table. Then it keeps reading, and at that point it says, well, 5 is not less than 5, so it doesn't do any more inserts, and it stops. And if you didn't know SQL, you might think this is what actually happened this way, but it doesn't. In reality, an SQL database engine will do the entire select first and then insert it all at once. So you would really, if you ran this, would just end up with 1, 2. No, actually just in 1, 2. Yeah, but this kind of illustrates the idea about how you might kind of use recursion to do something multiple times, even though it doesn't work. And it turns out that in a recursive common table expression is a little bit different, and it does do what I just showed you. So let's talk about recursive common table expressions. They have an unusual form. It's kind of a rigid format. it starts with the keywords with and sometimes the keyword recursive. I will go into that more in a second. And then you have the name of your little magical view, and it's got to be a union or a union all. Or in some cases, it always has to be a union all, depending on what engine you're using. And then there's two parts of this union all. There's the first query is kind of like your initialization step. I got another slide that's going to make this a little bit clearer in a second. And then the second one is a query that uses the common table expression exactly once in its from clause. Let's see what's coming up next. Oh, here's an example. Here's how we load the table T1 with the first 5 integers. So we say with recursive, C of X, I'm just making up some, you can be whatever name you want, C of X as select 1. So the select 1 is kind of seeding the recursion. So the first value we get is 1. And then we do the second part of the union all multiple times. And we say select X plus 1 from C. Notice we're using the common table expression exactly once in the from clause. It's very important. It has to be in the from clause, not in the subquery, right there. And then we start doing this recursion just like we did before, where it looked like we were moving forward. But in this case, it actually works. It works just like I showed you before, where it starts building up the T1 and it keeps reading and keeps adding to it and keeps querying itself at the same time. Okay, so one head just exploded in the audience, but we're going to do some examples, and hopefully this will become clear as we do it. And further on down, the body of the recursive common table expression, of course, is I'm using the common table expression C in a select statement, which is initializing a table. So that really is what you would type if you wanted to initialize a table with the first 5 integers. Now, yeah, quick question: what if I really needed a table with the first 5 million integers? Well, that's really easy to change. You just change the 5 here to 5 million. I put a low number in there just to make it. And so this is something that I use daily because my main primary use of SQL is testing SQLite. You know, that's what I do on a daily basis. And so in making test cases, I often like to have tables that have all integers between 1 and 1,000,000. This comes up for me a lot. Real world, maybe not so much, but it's fine. So here's the correspondence to that little thing I showed you before. Remember, I talked about the recursion thing, and I said this is not how SQL really works. But here's kind of the correspondence and the syntax for recursive common table expressions. The initial, where you initialize the table right there, is the first part of the union all, and then your recursion step is the second part right there. So it does this first part one time, and then it starts doing this one over and over and over again until it's done, until there's nothing else to add. So how is this useful other than, I mean, suppose you wanted to do something other than add. Well, I guess the next slide is, well, how does this work in other systems? Okay, if you're running an Oracle, the first thing to note is that you cannot in Oracle have select in an expression without a from clause. You have to say from dual, and dual is a magic table that's in every Oracle schema that contains a single row and a single column. A single row and a single column, they call it dual. I don't know. I don't know. And the other thing is that they do not recognize the recursive keyword. So you can't say with, you just say with. And so that's Oracle. Postgres is exceedingly dogmatic about following the SQL standard. And so in order to do a recursive common table expression, you have to use the keyword recursive. And that keyword also changes the semantics of binding and so forth. But I've never tested how that affects Oracle and so forth. But whatever, you have to say recursive if you want it to be a recursive common table expression. You also, in Postgres, are allowed, instead of just saying select one, you could just say values one. Those are equivalent. You cannot say values one in Oracle. You have to say select one for dual. And in SQL Server, you must also omit the recursive keyword. You cannot say values one, you have to say select one. I forgot to mention earlier that the recursive common table expression, the join operator here can be union or union all. If the usual case is union all, and that means it takes everything it gets. If it's just union, it's going to filter out duplicates. Turns out that SQL Server only accepts union all. It doesn't have the feature of filtering out the duplicates. So with SQL Server, you have to omit recursive, and you have to use union all, and you can't use values. So those are the kind of the syntax quirks. Notice that there's no way to write a recursive common. Oh, I've got SQLite. Yeah, with SQLite, the recursive keyword is optional. You can put it in, leave it out as you choose, and it does accept values. So notice that there's no way to write a recursive common table expression that will run on both Oracle and Postgres, or on Oracle and SQL Server, or on SQL Server and Postgres. But I worked really hard so that with SQLite, you can actually write a recursive common table expression that will run on SQLite and any one of those other three. So it's a little bit more forgiving of syntax. Okay, so a big use for common table expressions is to use the thing multiple times. So suppose we wanted to produce a grid of all possible tuples from where the values are from 1 to 10. We could do that this way, where the recursive common table expression is loaded up with all values between 1 and 10. But down here, I'm using it twice in the from calls. I'm using C twice. So it effectively builds a little temporary table that has values from between 1 and 10, and then does join on them to give me a kind of a matrix of all possible combinations there. Very useful property. What if, in all the examples I've shown you, an important thing to note is there was a termination condition on the second clause. So for example, I had the where x less than or equal to 10 here, or x less than 5 here. But here I've left it off, and I've moved it out to the outer expression. And so the question is, will this work? And the answer is sometimes it will, and sometimes it won't. And so it's kind of at the discretion of the query planner. This does in fact work on Postgres. Yes, it does. I tried it. It does work in SQLite. I think if I recall correctly, Oracle gave me a warning that I didn't have a termination recursion condition, and then maybe SQL Server ran for a while and it said the common table expression is too big. I don't remember. So what's happening here is, when I kind of described what was going on conceptually, the idea is that this loop runs, it builds up this table, and then you use the table in the statement below. And conceptually, that's what's happening. But the implementation might choose something different. In particular, the implementation might implement this in a way so that it doesn't create the entire table if you don't use the entire table. It only creates the parts of the table that you actually need. Now, the details of that, you as the programmer who are writing the common table expression shouldn't have to think about that. This is at the discretion of the query planner inside your database engine. But Postgres, I think it sets up a queue where it sets up the common table expression runner thingy object. It it's a demand thing. It's on demand. So the lower query says, okay, I need the first row. And then the common table expression runs and generates the first row. And then this guy says, I need the second row, and so forth. And so it eventually figures out that it's going to stop, and it doesn't actually generate all of the whole thing. So this is not recommended. Don't do this. Don't do this. But you can sometimes get away with it. All right, so here's some examples of how this might be a little bit more useful. Recursive common table expressions are useful for querying graphs. And I have a graph here, and it's an undirected graph, and I've got a table representation of it over on the side. So we see that so we've got the graph, and we've got, I call the fields x from and x2, because from and to are keywords in SQL, and that would cause problems, and I have to escape them if I just use them there. But x from and x2, and so for example, we've got an arc that goes from node 0 to node 2, which is right here, and I've also got an arc that goes from node 2 to node 0. So this is really encoded as a directed graph, but I've drawn an undirected graph. But it's a directed graph where the arrow, there's always a pair going in the other direction. So the question is, how I want to find all nodes that are connected to node 9. This might come up, for example, in querying your network topology. This might come up if you're doing an airline reservation system and you want to find, all flights that are reachable from Boca Raton or something. I don't know. So all nodes that are connected to 9, and this is the recursion we set. So we got this. We're creating a common table expression called con for connection, and it's got a single field ID, and we're starting at 9. So our initialization, we select 9. If there's an entry in this table with a value, that means that node is connected to 9. So 9 is connected to itself. We initialize it that way. And then we say select 2 from the connection, join to the link, where from is in the connection. So we're just adding new nodes in as we traverse the graph. And also we've done union here, because we don't want to get going in loops. If I'd done union all, it would start looping and making multiple entries of the same thing. We don't want that to happen, so I did union there. And so if you run this, you will in fact get output that says 9, 6, 8, 0, 2, and 3. And you can, and that's the order that it actually comes out in. And you can kind of see how that happened, because it started at 9 and said, okay, what's connected to 9? 6 and 8 are connected to 9, so they came out next. And then, well, what's connected to 6 and 8? Well, that's 0. And what's connected to 0, 2, and 3? So you can kind of see what it did. And it does, in fact, do that. Here's a slightly different graph. I just added a single edge that goes from 0 to 3. Let's find all nodes that are within 4 hops of node 9. And this would come up in like in an airline reservation system, where you want to find, you're leaving Charlotte and you want to find all the places that you can get to with only 2 connections. That would be like this. So you start with, now my table is the connection. We've got a connection to, this is the place we're connected to. This is how many hops we had to go through to get there. And so I'm initializing at 9. We didn't have to go through any hops at all to get to 9, so it's 0. So the initial value is 9, 0. I do a union all, and then I say the next link is where we're going to. We increment the distance, join on the connection where we're coming from, and where the connection is less than 4. Now there is some duplication here because there are multiple paths to get to the same spot, And so I have to add the distinct down here in the bottom. And sure enough, this shows me, it says 9 to 6 and 8, to 0, to 2, to 3, and to 7, and then it stops. And if I'd said down here, well, if I could have said select ID, comma, dist from con, and it would have shown me all the possible ways to get there with distances. But there's not a SQL standard way of saying distinct on. I mean, you can do that in Postgres, but I don't think you can do it anywhere else, can you?
No, but it's not standard. I put that, I had to document that.
Yeah, distinct on is a Postgres only thing. And if I had a distinct on, see, I could have put a distinct on ID, comma, distance, and then seen the distance for each one. There's a way to do that in SQLite as well, but it's also non-standard.
Yeah, because it wasn't clear like what distinct one did. Like,
Yeah.
we had the syntax, but we didn't explain what it was. Now you used union all here, and that's because you felt you limited enough on distance.
Well,
But you didn't need to, because I was thinking if you had, suppose you had a city that was reached.
you could put union here. You could
Because
put
I'm
union here.
thinking you might have a city that's reachable with one hop across two different cities.
Right. And so, this would get rid of that duplication for you right away. And you could certainly go ahead and put union here. I think what happened was when I was doing these slides in the previous one, I had just put union all, because most of the time you put union all here.
Yeah.
Because when you put union, that means the database engine has to do a little bit of extra work to filter out the duplicates. So it's not a lot of work. It doesn't really slow things down much, but it is extra work. So default to union all unless you really need it. And so then I came back and I changed this to union when I saw all the duplicates. And I just didn't change it in the other one. So here's a real world example of using recursive common table expressions. This is in Firefox. So, you know, all your bookmarks are stored in an SQLite database in Firefox. And the table that they're stored in, of course, your bookmarks are organized in a tree, in a hierarchy. And you can go in and drag things around and move bookmarks into different subfolders and so forth. And this expression is used to, let's say, well, the comment tells you, make sure we are not moving a folder into itself or into one of its descendants. So this is part of the operation when you're dragging a folder, or a file or a folder from one place to another. And it actually queries the database that stores all your bookmarks to verify that you're not creating a loop in your directory hierarchy using a recursive common table expression. I thought that was really cool when I saw this.
Very, very hard. The application level is a thing to do.
Yeah, this would be a real pain to do if you had to write application code. And so here's an example from Fossil where we're finding all of the descendants of a check-in, and we're storing their IDs in a table that already exists called OK. So actually, we're finding the first n-1 closest in time. And so once again, we're starting in a single node in a graph, and we're walking through a graph, filtering as we go, and then our termination condition is a limit of 30, or limit of n. So this is a real world example, but I want to get in and spend a little bit of time talking about, this is an academic exercise. I'm going to show you how to solve a Sudoku puzzle using a recursive common table expression. This is an academic exercise in the sense that this is not something that's really going to come up in your typical business application. But if you understand this, then you can say that you understand common table expressions. And initially, just for explanatory purposes, I'm going to start simple with just a Sudoku puzzle that has only 2x2 blocks instead of 3x3, and that keeps the problem a little bit shorter. And then at the end, it's just a matter of changing it to constants to go to 3x3. So we're going to represent the puzzle as a string, with each character in the string being a square in the puzzle. And we're reading right to left, top to bottom. So the first character of the string is 1, and that one's blank, so we put a period there, or a full stop, full stop, full stop, and then we read this one, this one, this one. Finally, we get to 2, and then 3 more stops, and then a 3, and then the 4, and then 3 blanks. So that's the format of our puzzle, and we want to fill in the gaps and find. Here's some preliminaries. We're going to need some auxiliary tables. We want a table that's just going to store our input, and I'll call it input. And we'll want a table that's going to give us all of our digits from 1 to 4. Do I need to go back up? You got some questions? Or you're okay? I can back up. If I'm going too fast, stop me. If I'm going too fast, stop me. So for right now, this is just a temporary step. We're gonna actually fold this all into the single expression in a minute. But just for conceptual purposes, let's start with 2 tables. One of them has a single row, and that is the input problem. And then another table has just our digits. And we're going to need our digits both as numbers and as characters. So this table is going to have 1 column for each. And I actually initialize the digits table with the digits 1, 2, 3, and 4 using a recursive common table expression here. So those are some preliminaries. Here's some more preliminaries of some functions that we're going to be needing. There's the instir function. I think this is a little bit different in Postgres. I think it's, how does it go? It's string, you do the same thing, but it's spelled out with syntax. Instir, I think, is a MySQLism, isn't it? Or is it an Oracleism? I don't know. Instir takes two strings, A and B, and it returns an integer where the integer is the index in the first string where the second string occurs. And SQL is 1 index base, so if it occurs at the very first position, it returns 1. And if it doesn't find it anywhere, it returns 0. That's the way instir works. I didn't make this up. I copied it from somebody else, so this is not an SQLism. This is not an SQLite-ism. So, for example, in the first one, we're asking for the first occurrence of a full stop, and that's in the second character position, because the first character position is taken up by 1. And in the second one, the first instance is at character position 7. And on the last one, there are no periods or full stops in the entire string, so it returns 0. Okay, so that's a standard function. All the SQL database engines have a function like this, though they sometimes call them different names. And then we have a substir function, which takes a subset of the string. And the string is in A, and then B is the first character of the substring, and C, if it exists, is the number of characters in the substring, or if C is omitted, it just returns the rest of the string, the tail. So, so here's the string right there. We want, starting with the 4th character, we want 3 characters. So 1, 2, 3, 4, and then we return 3 characters, and sure enough, that's what we get. And likewise here, we're going to start at the 13th character, and then we're just return everything else. And that's the 13th character, and it returns everything else. So those are 2 functions, and they all the database engines have these, just sometimes named differently. And now I'm going to, just for conceptual purposes, for right now, let's imagine we have a magical function called isValidSudoku. And this function takes 3 arguments. And the first argument is one of the strings that represents the Sudoku puzzle. And the second argument is a character position, or the second argument is a character, 1, 2, 3, or 4, or 5, 6, 7, 8, 9 if you're working in full size. And the third one is an insert point. And so if you insert that character into the middle of the puzzle at that point, is it still a valid Sudoku? And it's going to return true or false. It's a magical function. So if we have all of these things together, then this is a recursive common table expression that will produce an answer to your Sudoku puzzle. Let's work through it. So the recursive expression is Sudoku, and it's got 2 values, which are a puzzle, which could be incomplete, can have empty slots in it, and then X, and X is going to be the index of the first empty slot. And our goal, if you look down here at the bottom, is to return S where X is 0, meaning there are no empty slots. We want to return a completed puzzle. So we initialize our puzzle to J and the inster of J dot from input. So that's our initial state. It's the initial string that we had plus the index of the first unfilled slot. And then we're going to then here's our recursion step. We're going to insert into position x minus 1, or no, we're going to insert into position x a digit, and so we're getting all the characters before x, then we're replacing x, and then here's all the characters that occur after x. So in that blank slot, we're inserting a digit, and we're joining the input with all possible digits. So we're putting all possible digits in there. But we're only accepting those which end up being valid Sudoku puzzles. So it starts putting these strings in here, and every time it puts in a string, it knows it's a valid Sudoku puzzle, and the strings keep getting longer and longer, and finally it gets down to the end, and that's our answer. Of course, we can't actually run this because there are no SQL database engines that have an is-valid Sudoku function built in. So, of course, we also have those external tables. We could build them in as other common table expressions into the same SQL statement. So here's our definition of inputs right there at the top line. Rather than having a separate table, we're just going to make it a common table expression. Here's digits right here. Rather than having a separate table, we'll just make it another common table expression. And then down in Sudoku, we're using both input and digits, and we get our answer. So we've pulled it all down into one single expression. Now we still have this pesky is valid Sudoku. Here's the real magic right here. I'm not really going to go into this. This can be your homework assignment. You can go and get this and look at this and convince yourself that expression, which I've tinted blue, I don't know how well you can read it, but this expression right here will be true if and only if it's a valid Sudoku expression.
Percent modulus?
Yes, it is. Yes, it is. And that's the same in Postgres. Different operators apply in MySQL. Yeah. So yeah, it's really got three cases. The first case is looking to see if it's if there's two numbers that are the same on the same row, and then it's looking at two numbers the same on the same column, and then two numbers the same in the same block. Yeah, and
there would be a lot of tweaking to make it work on a 9x9.
not really.
Well, I can change the 4 to a 9.
Yeah, well, there's several changes like that, but I'll show you that in a second. So that does in fact work. And so, and down at the bottom, I'm going to make this change down at the bottom. I was clicking just the answer where x equals 0. I'm going to actually run this and show you all the outputs so you can kind of see what happens. And this is what actually happens. So we started out at the first one, and it tried to, kind of on the first iteration, it filled in 2, 3, and 4. And then on the next iteration, it got 3 and 4, or 3 and 4. You can see what's happening here. It slowly builds it up, and finally at the bottom, we get a single solution. Now, if the Sudoku puzzle had multiple solutions, you would have gotten multiple entries with 0 at the bottom. If it had no solutions, you never would have got an entry with a 0.
So if it would have had more solutions, on this one, I guess, you would have going back to, having like 15, 14 numbers until it gets zeros, right? Because it's kind of like a backtracking.
So if I started up here and I left out, if that 2 had been a full stop instead, a period, then there would be multiple solutions. There probably would be multiple solutions. I'm guessing. We could actually try it here if you want. There were probably multiple solutions, and so yeah, the list would be longer, and you'd have multiple answers at the bottom. All right, so This is allegedly the world's most difficult Sudoku puzzle. It's supposed to be really, really hard. I got this out of the Guardian newspaper or something. It's online. Just look for world's hardest Sudoku puzzle and it'll be there.
They're all equal to me.
And so I entered it up here. Here is the change, and if you could, I put a red tint on the part. This is the same expression. This is the same thing you saw before. I had to go to a smaller font because now we've got more stuff. And I put a red tint on the numbers I changed. And so basically, I just had to put in a longer string there. This changed from 4 to 9. And down here, we see lots of changes from 3 to 9, 6, and 27. Okay? But it's the same idea. Same idea. And then I ran that, and it took 208 seconds. It generated over 2 million intermediate solutions, but it did come up with a unique answer, which is shown right there.
So, okay, if a human is doing this, are they just kind of guessing as they do it, or do they?
Yeah, I mean, I think it's what.
No, humans would use logic and say this number has to be, or this slot has to hold a particular number.
I mean, there's a lot of easy Sudokus.
Yeah.
And on the easy Sudokus, there's usually multiple blocks that you can fill in by looking at it and say, well, I've already got a 9 up here, and I've already got a 9 on this row, so it's got to go in this column.
But this one is specially designed so that none of those easy things work. And you have to guess and you have to work through it, but it does have a convenient solution.
Similar to chess, right?
Yeah, you got to look way ahead. You got to look way ahead. Now, other people have published online similar sort of things where you can solve the 8 queens problem using the common table expression. On our website, we have to show you how to compute the Mandelbrot set using the common table expression and even print it out using ASCII art. You can do all kinds of things like that. They're silly examples. And these aren't useful. The useful ones are the ones I showed you earlier, where, like in Firefox, they're checking to make sure that you're not dragging a folder into itself. And that's what they question.
Would a common table expression be a solution when your data structure has an organization and it has underneath that owned organizations that point to the owner?
So the question is, so the question is,
and that can be a variable depth.
Right, so the question is, you have a tree, a tree of organization. Think of a hierarchy of, reports to you. You've got the big boss at the top, and then you have the vice presidents, and then you have the executive, and so forth. It works on down, and then Richard Hipp down here, and and so you might want to say, well, what is the total salary, what is the total salary of everybody in this organization, or what is the total monthly expense for everybody under John Smith's organization? Yeah, and so and you could use the recursive common table expression to go and walk that graph down and find who all is under him, both his direct reports and those that report to him and the ones that report to, and so forth on down. Yes, that's exactly what it's used for. It's very, very good for walking a tree that way. That's exactly what it's used for. Question right here in front.
Is this something that people would do to solve Monte Carlo modeling?
The question is this something people would do Monte Carlo modeling? I have never thought of that. Doesn't seem to me to be a particularly good thing to do right offhand, but if you've got an idea, I'm open to hearing it. Maybe so. I don't know. Mostly it's really used for solving hierarchy or walking a graph, walking a tree. I think in a version control system, you've got a tree of check-ins. You've got one check-in and then all of its descendants or all of its ancestors. It's really good at walking that tree and finding what they are. Question?
If I'm hearing half the databases can already do this type of graph search, why are graph databases called the range?
why are graph databases all the rage? You know, I haven't heard anything about a graph database in 10 years. Are they still all the rage? Am I just missing out on it?
Apparently they're coming in.
Apparently they're coming in, yeah. Well, you know, I don't know. Maybe
It's
the
essential
people who are
service.
inventing the graph databases do not know about common table expressions. Maybe. Do you have a comment on that, Bruce?
Yeah, I think we've seen this with Postgres where people will say, well, you know, can you do hash, can you do key value store, can you do document store, can you do graph store? And I'm like, yeah, you know, like we can do all those. I think that if you look at a graph database, it's really optimized to do the graphs. And, you know, I don't think Postgres is really optimized to do common table expressions because everything's kind of stored as a row and you've got overhead, there's transactions and all that other stuff. So the question is, and the same thing with pretty much any NoSQL solution, you know, do you need something that's absolutely optimized just to do key value store and that's all you want? Or do you really need something that can do all these things together and have, you know, transactional data store at the same time? And it's really a question of specialty.
So Bruce's answer was that a graph database is a premature optimization.
Yeah, very short, yeah.
Okay.
Can you put back to the slide where you had the URL for all of your slides?
Oh, that was the very first one. Yeah.
Home button.
Is there a home button here?
Right on the keyboard.
Thank you.
For the benefit of those on video, everybody's taking a picture of that slide. Question, sir?
If you were, like, if you wanted to take everything out of a database and make XML, would you use it? Would you use it?
Take everything out of the database and make it XML. Why would you want to do that? Oh, XML is just, that's so 2000, you know?
I think that they still use that.
JSON, yeah. I mean, there are people, you know, I hear a lot of people talking about, so we're just going to store it as a big JSON blob somewhere. Postgres is accommodating this now by having bJSON data types, you know, but really, and I guess there is some argument in favor of having higher storage, but a lot of people, they say, we're just going to store it in JSON and parse it. They're missing this whole query planner point. Because so many people, they're raised on everything has to be procedural. They don't really get the whole concept of a declarative programming language where you're just throwing the query over the wall and letting the database engine do all the work of programming for you. And they feel, and people just don't, they're not comfortable with it. They've never thought about it. Nobody's ever told them. And if all you've ever seen of SQL is pulling out records by their primary key, yeah, then storing things as JSON seems like a perfectly reasonable solution.
Now, this isn't for doing actual work. This is just for like moving some descriptions from one place to another.
And moving descriptions from one place to another, in other words, using JSON as an application file format. I like to, this is kind of getting off topic.
Yes, a little bit.
I like to advocate SQLite as an application file format because one, it is a single file. Updates are atomic and transactional. So that if your application file is a big blob of JSON and you're making a change to it and you lose power in the middle of that, you've probably just trashed your application file. But with a database, you don't have a problem. And it depends on your file system. No, probably if it's big enough, it's going to trash your data file. And especially if you're doing it, yeah. Anyway, but also you can add new tables. OpenOffice right here. You know, the file format for OpenOffice is a zip archive. I know that it has an ODP extension on it, but it really should be zip. And inside,
Same with the docx.
it's got a bunch of same with docx. It's got a bunch of XML, and then like every image and all these other resources are separate files within there. And so when I open an OpenOffice document, it undoes the entire archive and loads everything into memory, parses up all this XML. And so you know, it's not such a big deal with these nice modern machines, but on older machines and with the kinds of when I do a 200 slide talk, you open it and then you just wait, and you got this little bar that's going across as it's updating. Okay, all right, I'm loaded. And then I change one character and I press File, Save, and I got to write out 30 megabytes in order to change one character. If it's a database, though, you just read in what you need. You query for the first slide and it pops up immediately. And then if you change a single character, it just writes out that, the one little bit it needs to change. The rest of the file is unchanged.
So you're saying all the slideshows should be SQLite?
Yeah, I really am. There was a bug in OpenOffice, a pernicious bug. It was going on for ages and ages, where sometimes when you do a file save, it would just corrupt JPEGs that you had inserted for no apparent reason. And JPEGs on pages that you had not even edited. I've got 2 minutes. We'll talk about this afterwards. How about that? Any other questions?
No, it's fine.
Question.
What's the performance profile like with these recursive common table expressions?
What is the performance profile like of these common table
Looks like you're running
expressions?
a lot of selects. Now, is that equivalent to running a bunch of select statements itself, or what's going on?
Probably it will run faster than you could do it yourself on the application side. Now, there will be exceptions to that. It's kind of the difference between assembly language versus a high-level language. Okay? Doing work in Python on the application side, that's assembly language. Putting it in an SQL query is a high-level language.
I mean,
In theory, you can always do it faster yourself in assembly language. But in practice, you've got so much of it, you'll never beat the optimizer. So just do it in SQL. It's going to end up being better in practice.
It's a little more complicated than that, because when you're doing it yourself, you have the whole round trip network to get it back and forth. You've got the parsing of the each select that you have. Whereas when you're doing as a common table expression, that whole blob is being parsed once. It's one transfer to the application, and then it's one return of your result. You're never going to beat that if you try and walk a graph.
And for the audio, Bruce is pointing out that you also, if you're doing it with a common table expression, you don't have the round trip server time to take into account, and so that's going to add to your performance. So yeah, they usually work really well. Go. Do not premature optimize. Go with the common table expression first. And if it turns out to be too slow, then you can work on another solution. And we have 30 seconds. One more question. We're done. Thank you very much. Enjoy the rest of the conference.
access its individual dashboard, then click and drag to zoom in on choke points and get more detail. Comprehensive network data, including inbound and outbound traffic, is available on the Network tab, and disk writes and free space on the Disks tab, while the Process Explorer displays usage statistics for individual processes. The System Info tab shows listening services, active connections, and available updates. Adding Longview to a system is easy. Just click the button, copy the one-line installation command, then run the command on your Linux system to complete the process. The agent will begin collecting data and sending it to Longview. Then the graphs start rolling. Use Longview to gain visibility into your servers, so when your website or app heats up, it stays up.